This next part on logic design concepts focuses on sequential circuits. Okay, so far what we have seen has been combinational circuits, and in the combinational circuits we talked about gates, we talked about Carnot maps, we talked about upper level components such as let's say comparators, adders, and so on. But something common between all of those was was the fact that they never remembered anything from the past. But then in the previous section, we talked about the storage elements that could remember something from the past. Some data at some time can be stored in that element. Those are memory elements, and those are the bases, the same way the gates are the bases of combinational circuits. The flip-flops are the bases of sequential circuits, or they can be used as elements of sequential circuits. Just like combinational circuits, we have sequential circuits that consist of just gates and flip-flops, but then on the other hand we have higher level packages that have some functionality. For example, a counter is a package of a sequential circuit that can be used for doing some counting. So when we think about upper level design, we may think of taking some of the components such as adders, subtractors, counters, registers, and a mixture of combinational circuits and sequential circuits, or combination of packages and sequential packages, and put them all together. All right, what this section does, we talk about building sequential circuits first with basic elements like gates and flip-flops, and then we define other sequential circuits that play role of packages. All right, so we start with finite state machines, and we talk about designing state machines. We talk about Mealy and Moore. One hot realization of state machine is what we'll be discussing, and then finally we talk about sequential packages, a few of them, not a very extensive list of them. Any sequential circuit can be described as or can be modeled as a combinational circuit with some primary inputs, some primary outputs, some inputs that play the role of the present state of the circuit, and some outputs that play the role of the next state of the circuit. So separating this combinational circuit from everything else that you see around it, this combinational circuit is just like any other combinational circuit, can be designed using Carnot maps, Boolean algebra, any technique that we discussed so far, or it can be also described using, if it is a very complex one, using adders, comparators, and things. And then what happens is, what is now the present state of the circuit, okay, or what is now on these outputs, let's not call it the present state or something, what is now on these outputs here gets clocked into the flip-flops on the feedback path, and then what happens is this feedback will be going back into the input of the combinational circuit, and it provides the present state of the circuit. My combinational circuit will make decisions based on the primary inputs and also the present state of the machine. okay, or the present state inputs. And so if we look at it from this point of view, we have these primary inputs that come in, these present states that come in. The primary inputs decide on the primary outputs, and also decide on the what we call the next state of the machine, okay, or the next state of this entire circuit. Once the next state is decided, we wait for the clock. When the clock arrives, the next state will be clocked into the flip-flop, and it will provide, or it becomes the present state of this circuit. As soon as that present state becomes the input of the combinational circuit, this present state will further propagate this way, and will also propagate this way to create the primary outputs, and also to provide what will become the next state. Okay, so as you are seeing, I have both green arrow and the yellow arrow in the in both outputs, meaning that the primary outputs and the next state of the machine are decided by the primary inputs as well as the present state of the machine. And once this is decided, there will be one clocking. The clocking will take the what is called the next state of the machine and feed it back into the input. In designing this circuit, all I have to do is to design the combinational part, because the flip-flops are plain simple feedback lines. Okay, so you will be seeing, I'll be using the techniques I've already discussed, like the Carnot maps and truth tables and things like that, to design these outputs in terms of actually these outputs, let me do it this way, these outputs in terms of these inputs and these inputs. Okay, all right, and this one is next state. This one is, as mentioned there, present state. Okay, let's start with a very simple circuit. Actually, the circuit we are discussing is a what we call a sequence detector. A sequence detector is something like this. It has an X input, it has a W output, it has a clock input. The circuit is searching for a certain sequence of ones and zeros to appear on the input. For example, the circuit I'm describing now, it looks for 1 0 1 1 on the input. It means that if eventually I'm going to be using rising edge clocks, it means that if in 4 consecutive rising edges of the clock, okay, I find 1 0 1 1 on my X input, then the output becomes 1 and remains 1 for exactly 1 clock cycle. Okay, so let's look here. I have a 1 here on the rising edge of the clock. Okay, I have a 1 on I have a 0 on X on the rising edge of clock. I have a 1 on X on the rising edge of the clock. I have 1 on X on the rising edge of the clock, and therefore I have seen the sequence 1 0 1 1 on the rise and on 4 rising edges of the clock, 4 consecutive rising edges of the clock, and therefore as soon as the 4th clock ticks, my output right after the edge of the clock becomes 1, stays 1 for the complete duration of 1 clock, and then becomes back to 0. What if I receive a 1 0 1 1 and then another 0 1 1? Well, if you look here, in 4 consecutive clocks I have had 1 0 1 1. Okay, and here again in 4 consecutive clocks I have had 1 0 1 1. And since my circuit here is draw the circuit over here, is a circuit that detects 1 0 1 1 on the X input. Therefore this 1 0 1 1 as well as this 1 0 1 1 with an overlap of a 1 will also turn the output on, and therefore I have 2 pulses on my output. Alright, let's design this. Okay, to design this I start with what is called a state machine. The state machine searches for 1 0 1 1 on the X input. Okay, I start with state A. I'm saying while I'm in state A, I am looking for a 1, and therefore if I receive a 0, I'm going to ignore it, and therefore okay, if I receive a 0, I'm ignoring it, and therefore I don't change the state of my circuit. On the other hand, if I receive a 1, it is something worth remembering because it is in the direction of the correct sequence, and therefore I move 1 step forward or 1 state forward from state A into state B so that I do remember the 1 that has been received. So a 1 has been received in state B. On the side of your paper you write down B is the state that remembers a 1 has been received. What if I receive another 1? Well, another 1 doesn't really do me any good in the direction of finding 1 0 1 1, but then another 1 can also be regarded as the first one of the 1 0 1 1 sequence, the same as the previous one that was received, and therefore a 1 has been received, another 1 has been received, a third one, a fourth one. All of those don't change my state from state B because state B is characterized by a state in which a useful 1 has been received. All right, if we were counting the number of 1s, we had to change the state, but since I don't really care about the number of 1s, all I need is 1 1. Therefore state B is the state that I'll be staying in. So in state B, I will stay in state B as long as I receive 1. Okay. What if after 1 1 or 2 1 or 3 1s I receive a 0? Well, that's good because this is in the direction of the sequence that I'm looking for, and therefore a 0 takes me forward to the next state, state C. Okay. In state C, I will be looking for another 1 to take me forward to state D, and then another 1 takes me forward to state E, where my output becomes 1. The usual way of doing it is to take the proper sequence, take it all the way through, and then come back and fill in the blanks. Like the green lines I'm showing, go all the way through 1 0 1 1 and then come back and fill in the blanks. Now let's fill in the blanks. Well, we already talked about a 0 goes back to itself. If I receive a 1 on B, then a 0 takes me forward, a 1 feeds back into state B, because a 1 is all I need, not 2 1s, not 3 1s, not 5 1s. All right. A 0 takes me to state C. Now in state C, if 1 I go forward, what if I receive a 0? Well, 1 0 0 is not good because it doesn't really help me in any way towards finding the correct sequence of 1 0 1 1, and therefore 1 0 0 takes me back to the state A, this state here. That 1 0 0 is no good. I have to start all over again, and therefore I go to state A. For each state, because I have 1 input and the input can take either 0 or 1 value, I have to have 2 edges out of each state. Now I am in state D that I have received 1, 0, 1. Obviously, 1 takes me forward to state E. What if I receive a 0? Well, if I receive a 0, I haven't received 1, 0, 1, 1 that I was looking for. But then the last part of it, 1, 0 part, can be regarded as the beginning 1, 0 sequence towards the 1, 0, 1, 1 sequence. And therefore, if I receive a 0, I go back to state C, where state C remembers that a good 1, 0 has been saved. Once, so this is going back to this state. Once I go to state E, I have 1, 0, 1, 1. If I receive another 0, that is the 1, 0 part. If I receive another 0, it means that the 1, 0 can be used again, and therefore I go to the state where 1, 0 has been saved, which is the C state. On the other hand, if I receive a 1, 0, another 1, well, I only go to the state where a 1 has been saved, which is the state B. So the state B, you can call it got 1. This has got nothing. This has got 1, 0. This is got 1, 0, 1. Okay, and the state E is the one that has got 1, 0, 1, 1. And then go to these states according to the sequence that you have obtained so far. So this is my state diagram. The next step is to, and this is based on this, right? Based on this 1, 0, 1, 1, 1, 0, 1, 1. Yeah, that's based on this timing diagram. And if you trace this timing diagram in this state diagram here, you will see that you will get out of E, and then let's look. You will. This is where you will be when you are in state E, and once you are out of state E, a 0, a 1, a 1, a 0, a 1, a 1 will take you back to state E. Okay, so once you are in the state E with a 1, okay, once you are in the state E with a 1, another 0, 1, 1 brings you back to state E again with the 1 on the output. Alright, what's next? Let's build this circuit, and first I will turn it into what is called a state table. Well, state table is nothing complex. It's just, let me just draw it here, and then I go back to the next state, A, B, C, D, E. State table is something like this. For input 0, 1, if A is 0, go to A. If A is 1, if X is 1, go to B. For B, for B, input 0, go to C. Input 1, go to B. For C, input 0, go to A. Input 1, go to D. For D, input 0, go to C. Input 1, go to E. For E, input 0, go to C. Input 1, go to B. And then the outputs, all outputs are 0 except state E. Okay, and therefore this is my state table and my output table. And here is the same table that I was showing.